Okay, so let's move on to part 2 where we start to model our data. So we're going to start by modeling the hazard by using the sdreg command, and we're going to use an exponential distribution. We're going to estimate the mortality rate using this. So if we run the command sdreg with the option distexp, distexp stands for distribution exponential. This tells Stata that we want to fit an exponential model. And here we can see that we have the following output where we have only an underscore cons here and hazard. So this gives us the hazard rate across the whole of the population. So we should see that it's the same as if we write SD rate here, and we see that it is exactly the same as the rate that's output here. So it's just the rate across the whole of the time scale for the entire population. So if we now want to fit an exponential model adjusting for deprivation status, we can do that by including the dep command, the dep option, the dep variable in our command, and we use the I dot notation to say that this is a categorical variable. So if we do that, what we get out here is you can see that the table has changed from hazard to hazard ratio here. In fact, the cons output is not a hazard ratio. It represents the hazard rate within the reference group here, which if you can look at the deprivation groups, we don't have a dep 1, so the least deprived group. So the least deprived group is the reference category. So that's what the underscore cons refers to. It's the mortality rate in the first deprivation group, the least deprived group. And then the hazard ratios we get are all comparing each of the different deprivation groups to the deprivation group 1, the least deprived. So if we look at the most deprived, we can see that the hazard ratio is 1.37 for the most deprived versus the least deprived, meaning that the mortality rate is 1.37 times. The mortality rate in the most deprived group is 1.37 times that in the least deprived group. The question also asks us to write out the model formula for this model. This is in the solution, so you can go there and have a look at that. The next question, question 14, asks us to predict the hazard rates and hazard ratios from this model and plot them. To think about the assumptions we're making when fitting this model, and given our answer in question 8, do we think that these are reasonable? So let's first use the predict command. So what predict does is it uses the sdreg that we've previously fitted and tells it, okay, from this model, predict, and then we give the option hazard, so it knows to predict the hazard, and create a variable that's called hazard exp. So if we do that, then what we do is we have this hazard exp variable that's created, and then we use all of this to show our hazard rates. So we can run this, and what we can see is that the mortality rate per person year is flat across time since diagnosis for all of these individuals, for all of the deprivation groups. And we can see that we have that the rates are the highest for those that are most deprived, and then as we go down the deprivation groups, we see that the lowest is the least deprived group. So if you remember in part 1, we actually looked at some smooth rates, and we saw that this decreases across time. So actually the model assumption is that the rates are constant across time, meaning that these are flat. So we are enforcing this in our model. So actually, when we looked at the data, we saw that this decreases across its time. So perhaps this isn't a great assumption to use an exponential model and assume that the rates are constant across time. So let's look at fitting a Weibull model here by using the same command sdreg, but instead using the distribution Weib or Weibull option. And what we get out looks like this. We have a cons again here. We don't have any variables in this model. So this constant is the underlying rate. We have some other output here, which represents the shape variables that we're not going to go into. So what we can do is then predict the hazard rate from this model and compare with the unadjusted exponential model. And let's think about what assumptions we're making here. So what I've done is I've used the predict command again and told Stata to use this model that we have here and predict the hazard. And we're going to call it hazard wibe. And then we use this line command and tell Stata we want to plot the line of the hazard wibe by the underscore t, which is our time variable that is created using STSet. And then we get this curve that looks like this, where we see that we have a mortality rate per person year across time since breast cancer diagnosis. And this is for overall, so it's not presented by deprivation status. But we know that when we fitted the previous exponential model without any deprivation status, that we made the assumption that the rate was constant across time. And here, obviously, you can see that we're no longer making this assumption, but we are making the assumption that it has this constant decrease in function shape that is typical per the Weibull model. So perhaps this is a better fit when we think about those the crude or the smoothed hazard rates that we looked at previously, where we saw that this decreased over time. We can see when we look at this output that this is decreasing over time, but it's not exactly the shape that we had looked at previously. So let's then look at when we do want to adjust for deprivation status. So we use the sdreg command again, and we add this i.dep option, or that tells us that we want to include the deprivation variable. And now we have hazard ratios again here presented. And again, these are all with reference to the deprivation group 1, the least deprived. So if we look at the most deprived output here, we have a hazard ratio of 1.35. Previously, we had 1.37 in the exponential model. This 1.35 means that the mortality rate in those that are most deprived is 1.35 times that in the least deprived group. So if we want to compare the hazard ratios side by side, what we can do is we can fit the models again. And now I use this qui, or quietly, it's short for quietly, option, so that we don't have any output. So what I would do is run this command, and what it does in the background is it fits the model again, but it doesn't put out the output. And then I want to use this estimate store command. So this tells Stata that we want to take the model that we just fit and store it in this thing called exp. So I'm fitting the exponential model again, and then I'm going to do the same for the Weibull model and store those results in this thing called wibe. And once I do that, then I can use this command called est, or estimates table, and tell it that we want to look at the values that are estimated from the models saved in exp and wibe. And we use the eform command just to exponentiate those, so we get the hazard ratios. So if I run this, we should get some output here. Here we go. And now we can see the direct comparisons between the hazard ratios. So if we focus on these top four, these deprivation outputs, remember that this is comparing to the least deprived group, and you can see that they are quite similar in these two models, despite the underlying assumptions that we're making in the background. That is that the exponential model has constant mortality rates across the time scale, so they're flat, each of these rates. And the Weibull makes the assumption that we have some Weibull function, which is a constant decreasing function, as we just saw. So what we may want to do is think about, okay, we've made these assumptions about the underlying rates or base or hazard function. What we can do instead is we can fit a Cox model where we don't have to make any assumption about this underlying rate, underlying function. What we do instead is that we don't actually estimate anything about that. We'll just get out hazard ratios. So we won't be able to get the crude rates from that model, but we get hazard ratios. And if we're interested in that, that might be a good thing. So let's start by running a Cox model without any covariates. And in order to do that, what we do is use the stcox command in Stata to tell Stata that we want to fit a Cox proportional hazards model. But because we don't have any covariates, we have to use this estimate option here. So what we do is we run this like this, and you can see that there is absolutely no output. And if you're wondering why this is, then think about what the Cox model is doing. When we did this previously using STReg and had the exponential, the Weibull model, we saw that we got an estimate for cons, which represents some form of the baseline hazard function. But we know in the Cox model that we don't actually estimate the baseline hazard function. And that's the reason why we don't have any output here. So what we need to do is actually include covariates because we're interested in hazard ratios if we're fitting a Cox model. So now what we do is we include our deprivation status in our Cox model by including the i.dep variable here. And then we can get our hazard ratios out again. And again, this is all with reference to the deprivation group 1, the least deprived group. And we can see if we look at the hazard ratio for the most deprived, that the mortality rate in the most deprived group is 1.35 times that in the least deprived group. And again, we can use our estimates store and estimates table command here. So we tell Stata that we want to save the values from this model in something called Cox. And then we want to display them side by side with the values from the exponential and the Weibull model. And here they're not quite displayed side by side, but you should be able to see that we are still comparing the top here, 1.08 to 1.08. And we can see that these are still very similar between the different models. So essentially, independent of the assumption that we're willing to make, even if it seems to be potentially a bad one in the exponential or the Weibull model, that we would still get the same conclusions. The results are very similar. So that's quite reassuring. What we can do is if we want to predict the hazard ratio, we can do that from our Cox model, and we use the predict command again and use this option, HR standing for hazard ratio, where we create a variable called HR_Cox. So let's do that. Then we have this variable HR_Cox in our data set. And then we use this command here to plot the hazard ratios across time for the different deprivation groups. So you can see here I've got different line commands here where we plot the hazard ratio Cox, the variable we created, by the timescale _t. And we say we want to look at it within these different deprivation groups. We have some other options here for the legend and for the x-axis and the y-axis. So let's have a look what we get when we run this. And we basically get the exact same values across the timescale as which was outputted from the STCox model. And this really illustrates the proportional hazards assumption here, because if you remember, the proportional hazards assumption is that the hazard ratio is constant across time. And we can see that here. Remember, now this is the hazard ratio and not the hazard rate. The Cox model doesn't directly estimate the underlying hazard function, the hazard rate. So this is now on the hazard ratio scale. So remember our y-axis here when we're thinking about this. And we can see that these are flat, is constant across time. This is the assumption that the Cox proportional hazards model makes. So what we then do is we're asked to use the stcurve command to plot the hazard functions by deprivation status. So remember that these are estimated using smoothers post-estimation. So when we fitted our Cox model, we haven't estimated any underlying hazard functions, but now we're going to do some extra work outside of the model, using the models, the information from the model, and then say, let's try and actually do some estimation to see what this looks like. So what we do is we use the command stcurve, and we say we want to plot the hazard by using the hazard option. And then we tell Stata that we want to look at this at the different deprivation levels, so at dep 1 to 5. and we just have a name here for this curve. So let's have a look what it looks like here. And we can see something that looks very similar to what we saw in our first part of our tutorial, where we plotted the smooth rates over time. We see that the rates shape looks as though it's decreasing over time. This is quite different to what we assumed in the exponential, where these were flat, and from the Weibull model, where we saw this Weibull typical shape. So the next part of the command that we have in the do file is actually exactly the same, except we tell Stata to log the Y scale. So let's have a look what happens here. What we can see then is that the difference across the whole of the time scale between these lines is constant. We fit the models on the log scale. So actually, when we look at the command, the results on the hazard scale, or when the Y scale isn't logged, we don't see this constant difference between these lines. But here we can see that, and that represents again the proportional hazards assumption, that when we take the ratio of these across any time point, we see the same value. So the last part of this section asks us to split the follow-up time at 2 years post breast cancer diagnosis and include this variable in an exponential model. And then it asks us, does this model assume proportional hazards or allow for non-proportional hazards? So let's first split our data set, and we can have a look at what that means. So we tell Stata that we want to split our data set, or our time scale, by using stsplit command, and we create a variable called fu follow-up. And we tell Stata that we want to split our time at 0 to 2 years, and then 2 to 10 years, because the end of our follow-up is at 10 years. So if we do that, it tells us that we haven't used an ID variable. So let's go back to our stset command. So I actually used this stset command where we haven't told Stata what the individual ID is. So this is an important thing to note, that you can run the stset command like this without the ID variable, it will work. But if you want to use stsplit, you have to tell Stata what is the variable that identifies which individuals are different from each other. So if we run this again, now I've included the ID variable, we shouldn't have a problem in running this stsplit command. And you can see that we've actually created some observations here. Maybe we can take this opportunity to have a look at some of our variables. So if I just look at T0, T underscore D in 1 to 10. Let's see here. So if we look at the first individual, the first 2 lines now represent the first individual. Previously, we had 1 line, 1 row per individual. Now we have potentially up to 2. So for this first individual, the first line represents the part of the time where we follow them from 0 at diagnosis until 2 years. And at that point, they were censored. They didn't have an event of interest. The second line shows where we follow them from 2 years, so at this split point, until their exit time at 9.941 years, at which point they also were censored. They didn't have an event, or they didn't die at the end of their follow-up. If we then look at the observations for row 3 and 4, these both correspond to the same individual as well. We can see that their ID variable is the same. The first row follows them from 0 to 2 years again. And we see that at the end of that period, they were censored. And then at the cut point at 2 years, we follow them from 2 to 4.55 years. At the end of that time point, they had the event of interest. So we can see that this is split. The time scale is split into 2 different rows for each individual. And if we look at this individual here, row 7 in our output, we actually see that they were only followed until 0.45 years, at which point they died. So this means that they actually aren't split into those two different rows because we only have up to 0.4 years. So they only contribute to that 0 to 2 time split. So this is what SC-split is doing in the background. It's expanding our data set to represent those different time frames. So what we can do is we can use the sdreg command and include this in our model. And then what we get is we would get almost the same output as previously, but now we have this extra thing here where we see the effect of this follow-up time. So this actually gives us the hazard ratio comparing the first interval to the second interval. So what this means is that the mortality rate in the second interval from 2 to 10 years is 0.66 times that in the first interval from 0 to 2 years. Now, this shouldn't be so surprising because we did see that the rate was much higher early on in our time scale. But the question was, does this model assume proportional hazards or allow for non-proportional hazards? And this is really important to think about. What we do in this model is we allow the baseline rate to change depending on whether you are 0 to 2 years or 2 to 10 years. So it means that the rates will change. So we will see within each deprivation status that we can have a different rate within that 0 to 2 years than in the 2 to 10 years. But the hazard ratios are still constant within each of these. So we still have a constant hazard ratio across time. It's a really important distinction to make that the rates are allowed to change now according to this 2-year split, but the hazard ratios are still constant. And if the hazard ratios are still constant, that means that this is still a proportional hazards model. We are not allowing for non-proportional hazards.